Hi, I'm Bob. Welcome to Introductory Econometrics course. Let's find answers to the computer exercises for Chapter 13, Pooling cross-sections across time, simple panel data methods. In the textbook Introductory Econometrics, a modern approach to 7th edition by Professor Jeffrey Woodridge. In the first computer exercise, we estimate a model explaining the total number of children born to a woman. In part 1, we test whether the living environment at age 16 affects fertility. The base group is the large city. The dummy variables for small cities, towns, rural areas, and farms represent the other living environment. The null hypothesis is that the coefficients on these dummy variables are all 0. We use the test command in Stata to do the f-test for their joint significance. The F statistic is 1.16, and its p-value is 0.33. The dummy variables are jointly insignificant at any conventional level. It implies that the living environment at age 16 does not affect fertility. In part 2, we test for the joint significance of the region dummy variables. The F statistic is 3.01, and its p-value is 0.029. The coefficients on the region dummies are jointly significant at the 5% level. It implies that the region of the country at age 16 affects fertility. In part 3, let mu be the error term in the population equation. Suppose we think that the variance of mu changes over time. A model that captures this is to regress mu squared on the 6-year dummy variables. We can test for the heteroscedasticity in the error term using this model. In Stata, we use the predict command with the residuals option to obtain the residuals of the model. We name the residuals muhat. Then we generate the squared residuals. Next, we regress the squared residuals on the 6 dummy variables of the years. The null hypothesis of the f-test is that the coefficients on the dummy variables are all 0. In other words, the null hypothesis implies that the error term from the original model is homoscedastic. We can read from the result window that the F statistic for the overall insignificance is 2.90, and its p-value is 0.008. Or we can use the test command to do the f-test. We get the same result. We reject the null hypothesis of homoscedasticity at the 1% level. The variance of the error term from the original fertility model changes over time. Therefore, it's better to report the heteroscedasticity robust standard errors for the estimates. In the last part, we add the interaction terms between education and year dummy variables to allow the educational effect to change over time. The coefficients on the interaction terms represents the change in the educational effect on fertility over time. For example, the coefficient on the interaction term between education and year 84 is minus 0.176. It means that compared to the base year 1972, education had a more negative effect on fertility in 1984. The F statistic for the joint significance of the interaction terms is 1.48 and its p-value is 0.18. The interaction terms are not jointly significant at the 10% level, but some interaction terms are individually statistically significant. The education effect is not constant over time. Let's do computer exercise 2. We estimate a model explaining lwage in terms of education, experience, union membership, gender, and a year dummy. In part 1, we need to interpret the coefficient on the year dummy variable y85 in equation 13.2. We can write down the partial effect of the year dummy on the lwage. The difference in the lwage between the year 1985 and the base year 1978 is delta 0 if the education and the female are both 0. In other words, the coefficient on y85 is the percent difference in wage over time for men with 0 years of schooling, which is not interesting. In part 2, holding other factors fixed, what is the estimated percent increase in nominal wage for a male with 12 years of education? Propose a regression to obtain a confidence interval for this estimate. The percent change in wage for a man with 12 years of schooling is delta 0 plus delta 1 times education. Plug in the estimates and we obtain 0.339. He is estimated to have a 33.9% or more accurately 40.4% increase in wage in 1985 compared to 1978. There are at least 2 ways to get its confidence interval. One way is to use the lincom command in Stata to compute the estimates, standard error, and confidence intervals for linear combinations of coefficients. We type lincom followed by linear combination, the partial effect of y85 on wage for 12 years of education men. The second way is to generate a new interaction term, y85 times education minus 12, and then replace y85 times education with it. The coefficient on y85 delta 0 is the percent increase in wage for men with 12 years of schooling. From the estimation result window, we can find the same result as using the lincom command. The estimate is 0.339. The standard error is 0.034. The 95% confidence interval is from 0.273 to 0.406. In part 3, we re-estimate the model with the real wage instead of the nominal wage, which coefficients differ from those in equation 13.2. We could not find the wage variable in the dataset, but we can generate it from the log wage variable. Then we can generate the real wage variable. That is, to divide wage by 1.65 for the year 1985. After that, we can generate the log real wage variable and use it as the outcome variable in the regression. The estimates remain the same, except for the coefficient on the year dummy. In part 4, we are asked to explain why the r-squared from the regression in part 3 is not the same as in equation 30.2. We can write down the formula of the r-squared. In the real wage model, the total sum of squared is 284, while it is 319 in the nominal wage model. The sum of squared residuals is the same in both models. It results in a larger r-squared in the nominal wage model than in the real wage model. We will describe how union participation changed from 1978 to 1985 in part 5. We can use the by sort prefix and the summarize command to find the information about the union participation for 1978 and 1985. We type by sort Y85, followed by a colon, and summarize union. Another command to obtain the same information is to use the tabulate command with the sum option. Tabulate is used with the dummy variable Y85, and we put the union in the parentheses. In 1978, 30.5% of the workers belonged to the union, whereas in 1985, 18% of the workers were union members. There is a drop in union participation over time. In part 6, we test whether the union wage differential changed over time. We add an interaction term between the year 95 and the union membership to the model. The union wage differential was 0.202 in 1978, and it reduced slightly in 1985 by 0.0004. The change is practically tiny and statistically insignificant at any reasonable level, with a p-value of 0.995. It suggests no change in the union wage premium over time. In part 7, we are asked whether the findings in part 5 and part 6 conflict. They do not conflict because people might leave the union after 1978 for reasons other than the wage differential. A smaller percentage of workers belong to the union in 1985 and still enjoy the same wage premium. Let's solve computer exercise 3. We estimate a model relating the house value to the distance to an incinerator. In part 1, we consider the model and find the psi of delta 1 if building the incinerator reduces the value of homes closer to the site. Before building the incinerator, the dummy variable y81 is 0, and the distance effect on house price is beta 1. After building the incinerator, y81 is 1, and the distance effect on house price is beta 1 plus delta 1. The difference between them, delta 1, is the incinerator effect on house price. If building the incinerator reduces the value of homes closer to the site, delta 1 should be positive. If beta 1 is positive, it means before the construction of the incinerator, the houses in the location far away from the site where the incinerator is going to build had higher prices. In other words, the incinerator was chosen to build in an area where the houses were less valuable. In part 2, we estimate the model and try to interpret the coefficient on the interaction term. The estimated equation is as follows. As mentioned in part 1, the coefficient on the interaction term, delta 1, is the location effect of the incinerator on the house prices. Since both are in logarithms, the coefficient is the elasticity. A 10% increase in distance to the incinerator is estimated to increase the house price by only 0.5%, holding other factors fixed. The effect is not statistically significant at any conventional level, with a t-statistic of 0.59 and a p-value of 0.556. It implies that the incinerator has no causal effect on the home value. In part 3, we add the characteristics of the house to the model. It does not change the conclusion in part 2. The incinerator effect on the housing value is still tiny and statistically insignificant at the 10% level against a two-sided alternative. As in the textbook, we should consider using a dummy variable to describe the distance to the incinerator, which leads to a significant coefficient. In part 4, why is the coefficient on log distance positive and statistically significant in part 2 but not in part 3? What does this say about the controls used in part 3? The coefficient on the log distance captures the location effect on house value without the incinerator. The effect becomes much smaller and insignificant when the house characteristics variables are added to the model, because these explanatory variables are correlated with the log distance variable. The house price is explained mainly by these new explanatory variables, and the location explains little of the price variation. Let's go to computer exercise 4. In part 1, we use the data for Kentucky. We estimate equation 13.13, adding as explanatory variables male, married, and a full set of industry and injury type dummy variables. How does the estimate on the interaction term change when these other factors are controlled for? Is the estimate still statistically significant? We re-estimate the model with additional explanatory variables, male, married, and the injury and industry type dummies. We can store the result by the estimates store command and compare the results using the stab command. We find that the estimate on the interaction term becomes slightly larger after controlling for these factors from 0.191 to 0.231. The effect is still statistically significant at the 1% level. Part 2 is about the small r squared. The r squared equals 0.04. It means the explanatory variables in the model explain only 4% of the variation in the outcome variable. A small r squared does not mean the model is useless. If the estimate is unbiased or consistent, we will obtain the causal effect of an explanatory variable on the outcome variable. In this case, the difference in differences estimator on the interaction term will likely to have a ceteris paribus interpretation because the parallel trend assumption tends to be satisfied after controlling for the other factors. We estimate the model using the data for Michigan in Part 3. Compare the estimates on the interaction term for Michigan and Kentucky. Is the Michigan estimate statistically significant? What do you make of this? We use the estimate store command to store the estimate results for each model, and then use the stab command to display the estimates in a table. We find that Michigan's estimate on the interaction term is similar to that of Kentucky, but the standard error doubles, leading to a smaller t-statistic and an insignificant estimate. One reason is that the number of observations in Michigan is much lower than in Kentucky. Thank you for watching this video and subscribing to my YouTube channel. See you next time.